This is an application problem. In this problem, we're told about a cup of coffee. I like coffee, so this is an important problem to me. This particular problem deals with the rate at which coffee cools. And the mathematical model for coffee, for a liquid that cools, may not be in fact linear. It depends on what kind of container it's contained in. But in this particular problem, this turns out to be a very key observation, that the relationship is linear. And the data that we're given here is that the coffee starts out at 150 degrees, at least 5 minutes after it's poured. It turns out to be 150 degrees, and then 25 minutes after it was poured, so 20 minutes later, the temperature is down to 120 degrees. And we're asked to express the temperature as a function of time. Now, we're not required to graph this problem, but when there's a linear relationship, the graph can often lead me right to the formula for the line, and therefore the function I'm looking for. The wording of the problem says we want to express temperature. Let's use a capital T for that as a function of time. We'll use small t for that. And if it's a function of some variable, then that variable goes on the horizontal axis. The function's name goes on the vertical axis. So we're going to let t equal the temperature, capital T, at time little t. All right, and the units on capital T will be degrees Fahrenheit, and the units on little t will be minutes. All right. And again, we weren't asked to graph this, but let's go ahead and do that. 5 minutes after the coffee was poured, so that's at time t equal 5. The temperature was 150 degrees. So let's put a mark up here and call that 150. So that is a data point for this particular linear relationship. And then 25 minutes after it was poured, so over here at time 25, the temperature is down to 120, so it's fallen down to 120. All right. And we're told it's a linear relationship. So if I connect these two dots and extend off, that is the graph of the function that I'm trying to come up with. All right. And analyzing lines is fairly straightforward. Once you see the graph, you need the slope. The slope deals with the rise and the run. This is going to be a rise of negative 30 and a run of, let's see, we're going from time 5 to 25, so that's a run of 20. So my slope, which is often used, represented by the letter m, is my rise over the run, and this is equal to negative 30 over 20, which simplifies to negative 3/2, or negative 1.5. Negative 1.5. So it is a negative slope, which I would expect. And the interpretation of this, again, means that for every minute, the temperature is falling, that's the negative sign, by 3/2 or 1.5 degrees Fahrenheit. All right. Now to find the equation of the line, I'm going to use the point slope form. So y minus y naught is equal to m times x minus x naught. That's the point slope equation. And to use this, you need to plug in the value for the slope and one of your data points. Now, in our particular function, capital T is our y values. And the data point, we can use either one. Shall we use the first one here? At time t equal 5, the temperature is 150. So I use the y value 150, which means I now have to use the t value 5. The slope's negative 3/2, and we're using the variable t for our independent variable, and that occurs at time 5 that we have 150 degrees. So if we solve for capital T now, we have our function. This is the equation for that line, and so this gives us the linear relationship between temperature and time. So if I solve here, I'm going to just send the 150 to the other side. I got minus 3